as you will see, this is compatible with our view, our interpretational view, because it's a view of a closed system perspective on the coherence. Well, first I will talk about, I will recall some things about environment-induced decoherence and its problems. I will discuss what are reduced states, what is the coherence in closed system that we proposed, and then how this view solves or dissolves, sometimes solves the problems of environment-induced, and how this links to interpretation and quantum information, if we have time. First, the environment, according to environment-induced decoherence is a process that results from the interaction of the system with the environment. We have heard this many times. So we have the system, the reduced state of the system that reduces, that we trace off the degrees of freedom of the environment, and this, in certain cases, after a long time, a time longer than the decoherent time, goes to a diagonal state that defines the classical-like observables. What's the problem? It cannot be applied to closed systems. Which closed system? For instance, the universe. It offers no criteria to define the open system. It does not define classicality in a univocal way, and it cannot explain how a system can have at the same time, like this, certain classical properties or certain quantum properties, okay? We will come back here after the at the end of the presentation. So, what are reduced state? Because this is very important. According to Amnes, decoherence is a particular case of irreversibility, and I want to make a parallel with irreversibility in classical mechanics. In the classical case, when we are in the Gibbs approach in Kopman's formalism, we have the state that evolves unitarily and certain coarse-grained states that may evolve non-unitarily. In the case of that the system is unstable enough, I mean, it is mixing, this can reach a final state of equilibrium. And the relationship here is coarse-graining. What happened in the quantum case? In the case of the coherence, we have the state, the quantum state that evolves unitarily, and we have the state of the open system that may evolve non-unitarily. And what we say is that here there is also a relationship or relation of coarse-graining. So coarse-graining represents, in general, we used to see coarse-graining in the classical case, so maybe we make a partition of the classical space phase. Well, this is a particular case, but in general, coarse-graining is something that represents a restriction on the access to the system. So, and it is represented by, in general, by an operator, a projector, a projection. So, we have proved in the paper that this is a coarse-grained state. I mean, this is not a quantum state in the same sense that this is not the real state of the system, the classical statistical system, but a coarse-grained state. And for this reason, it can evolve non-unitarily. So, what's happening in closed systems? If we have, in a classical case, we have a coarse grain, and we can show that, we can prove that for certain observables, the expectation value of the state in those observables is the same that the expectation value of those observables in the coarse-grained state. This is the trick of making a coarse graining in this case. What happened? These are different, but these are different states, but for this viewpoint, I mean the viewpoint of those observables, they work in the same way. In the quantum case, it's the same. I have the reduced state, and for the observables belonging to the system, open system, I mean, the part of the closed system that I'm looking at, so the expectation values are the same for the complete system and for the reduced system, the complete state and the reduced state. So if we make a generalization, and this is the trick here, if we make a generalization, now we can talk about a generic coarse-grained state that arises as, but is defined by selecting certain observables that are relevant for us and that satisfy that the expectation values are the same. But which is the difference? In this case, the observables that I select are the observables that define a subsystem. They have to be all the observables on Hilbert space. I mean, in this case, this is not necessary. I can select the set of observables that I'm interested in that particular case. So, from this closed system approach to decoherence, we first select the observables that are relevant, the relevant observables. Then we compute the expectation values as always. Then we study the time behavior of the expectation value, and we see if that expectation value finally settles down in a final value, in a value, not final, in a value that can be computed as if the state were diagonal. Then we can define the coherent time and the preferred basis by analyzing the characteristic decaying time of the expectation value. This expectation value will have a diagonal part and non-diagonal part. After a decoherent time, we obtain only the diagonal part, and after a relaxation time, finally, then we obtain a final constant value. This is the relaxation of the system. What I want to say is that the case of self-induced decoherence, environment-induced decoherence, is a case of this situation. In this case, the relevant observables are the observables of the open system. The expectation value are computed like this, as always, but it is a particular case of the black formula. Then we make this, we expect this kind of evolution, and finally, when we can obtain a diagonal state that after a decoherent time, that finally after a relaxation time settles down in a final state. Why we say that this solves or dissolves the problems? First, do you remember, this cannot be applied to closed system, for instance, the universe. Zurek himself says, the universe as a whole is still a single-sense entity with no outside environment, and therefore any resolution involving its division into a system is unacceptable in a sense, in a conceptual sense. Well, this view is a closed system approach. It can be used to study the coherence in closed systems. For this reason, it can be applied to cosmology without problems. We can decide only, we have to decide which kind of observables we want to study in each case. In this case, the traditional view offers no criterion to define the open system, Zurek again. In particular, one issue which has been often taken for granted is looming big as a foundation of the whole decoherent program. It is the question of what are the systems which play such a crucial role in all the discussion of the emergent classicality. This issue was raised earlier, but the progress to date has been slow at best. In our case, there is no absolute criterion to define the open system or to define the observables of interest. Why? Because the coherence is a relative phenomenon. It depends on how I partition the whole system. This is the answer to your previous question. It depends how I introduce a partition into a closed whole system. Third, it offers no criterion for classicality, and this is interesting, but some things like that may happen, and we have shown that in a paper. Given a closed system, it may be the case that you have the closed system, take this as a subsystem and this as the environment, and this becomes the diagonal. Let us suppose that this subsystem in this partition becomes classical. This other also becomes classical, but the union of both does not become classical because this system does not decohere. And this is, we think, it should be clear because a system is given by the observables, and the observables are the observables of one subsystem, the other subsystem, are all the cross products we can make. So, we know that in quantum mechanics, the whole is not the sum of the parts. So this is something that is clear from foundations, but it cannot be accounted for from the traditional view that conceives that the coherence applies to systems, even if open. So, if these two become classical, but this does, the whole don't, is something very strange, that in that case, we have no dotted problem, because this view, our view, defines univocally the set of the classical behaving observables. In principle, we can take one observable, one by one, and we can see if these observables regarding the set of relevant observables, I can take I can take each observables and I can say if that observable decoheres or not. What decoheres are the observables, not the system. Finally, since it is supposed that the system is what decoheres, the traditional view cannot account for the coexistence of classical and quantum properties in the same system. For instance, let us suppose that I have this kind of transistor that has some classical and quantum properties. You have only two cases, or the quantum system or the quantum state of the open system becomes diagonal, the system behaves as a classical object, or if not, the system behaves as a quantum object. And we want to say that in the same system, there are some properties that behave classically and some properties that behave quantum. So we can say that because we can explain that an object might have classical-like properties and non-classical-like properties at the same time, because what decoheres and became classical is not the system, but each one of its observables. Two final remarks. This is compatible with our model Hamiltonian interpretation. Of course, why? Because our interpretation is also a closed system interpretation, and from our viewpoint, the quantum system is closed, and the states are states of closed systems, and it's also compatible with certain relative view of quantum entanglement and discord that we hear tomorrow by Guido here, and well, thank you again. Ahora puedes,
I guess
you can answer.
I'm not sure. So you can invoke decoherence to do different things. So I'm assuming the kind of Zurich worry, the first worry that the decoherence is not applying to closed systems like the entire universe. The worry there was when you, maybe this is wrong, because I don't know, I don't have the full context, but I thought that the worry was supposed to be something like if you wanted to use decoherence on its own to solve the measurement problem, without, say, using decoherence as part of a many worlds framework or something like that. If you want to use decoherence alone to solve the measurement problem to get determinate measurement results, then you're presupposing that there's some external environment, and so if you want to get like a precise fact about the state of the universe and what like the positions of all the particles in the universe are or something like that, you can't use decoherence to do that if you're not. But I feel, I don't see how, if that's, I mean, you're a modal person, so you're not using decoherence to solve the measurement problem.
Absolutely. Because,
I don't even know why you need an answer to that.
No, the fact is, I think that I understand you, because if you don't work especially in the coherence, in general, it's true, in foundations, the coherence has been used to solve or to give an answer to the measurement problem. I think, with many other things, just from the very beginning, that the coherence doesn't solve the measurement problem. So, not the traditional view, not our view. So this is not a, no. The fact is that from how do you explain how certain systems, say them, observable, we say, behaves as if they were classical. In what sense? In the sense that they give expectation value as if they were in classical states.
Okay, but then I don't understand what the problem is with the environment. Because you're just partitioning the system in some way anyway. So
no, but one thing is to partition a system in subsystems. That means that you have to retain the structure of a Hilbert space. I can choose a group of observables that is not enough to define a Hilbert space. So it's more general. This is the point. This is, I think that this is the trick. I don't know if you want to say.
Can you explain that? Just why, what was he worried about? Why would you care about doing that for the entire universe? Like, why would you, just for ordinary purposes, if you're not trying to have some kind of objective metaphysics, why do you care about the whole universe?
Well, I care because if I think that the coherence, in a certain sense, explains the classical-like behavior of certain somethings, that classical-like behavior cannot depend of that the system has an environment to look at, because if this were the case, the universe would never decohere and would never never behave as classical-like. This would be the idea. I don't know. ¿Quién fue primero? I don't know.
Just a small physical example to answer your question. Even if you don't use the coherence to explain the classical limit, you have to take into account that there are certain phenomena in which decoherence takes place, even if it does not explain the classical limit. For example, when you try to build a quantum computer, decoherence is a real physical phenomenon. And you still have to acknowledge that this is going on.
You cannot build, if there is decoherence, you cannot build it.
No, of course, yes. So you try to do it on the lab and you find the coherence, right? You are not using it to explain the classical limit. You are saying, well, there's something physical going on and I want to explain it.
This is another reason. I mean,
There are two ways in which you can deal with the coherence. As a physical process, which does not explain the classical limit, or?
The answer that Federico says that you can be interested in the meaning, I mean, from a foundational viewpoint, from a conceptual viewpoint, on the coherence, even if you are not interested in the classical limit, because the coherence is a very, very important process for physics today. So we want to understand it.
For what it's important?
Why is it important? Yes. It's important because we want to prevent it, to make a computer, quantum computers. Well, this is a very, very important in physics now. It's very, I mean, it's something that is very studied. And you know, it's important. I mean,
since this is a more general formalism, you can identify some. No.
no. Sí.
Because this is a more general formalism, you can identify some cases of decoherence in our sense that you cannot study with the other formalism. For example, when a system doesn't become totally classical, you can, with this formalism, you can identify some observables that does not decohere, or another yes, and in this way you can form a set of observables that remains quantum, and this can be useful.
If you want to.
I understand now, because when you want to build a quantum computer, you have to make sure you're isolating it from
Absolute. You need.
So
you need that things happen.
You have a definition of in what sense you have a coherent.
Okay. Yeah.
Let's separate the conceptual issues. I mean, the solution of the measurement problem, which is something which you appeal to model, I would appeal to Bohm. But then concerning the technical core, I mean, I have no objection whatsoever. That's actually what we do in statistical mechanics. That means,
I love you. You know, to publish this in physical journals, it's terrible. Because when you say this, everybody says that you are wrong, because anybody knows that the coherence is the result of I tell you.
Let's not play with names. Let's forget the coherence. What is the point? The point, you have a closed quantum system. For instance, a gas in a box. Okay. Then if you have a gas in a box isolated from the outside, as a statistical mechanician, I would like to derive Boltzmann equation. When I derive Boltzmann equation, I do exactly like you do. I mean, I take a coarse-grained description in terms of particle number. And then of course, the only objection is that there is some problem with time. That means you have to take some limits. Otherwise, a gas in a box is described by a 5-dimensional Hilbert space. You have a Poincare cycle. That means after a certain time, things keep repeating. To really extract the classical behavior, you need to take some limit.
Yes,
that's
of course.
what Boltzmann did and what we do in the quantum case. But at the end of the day, when I say how could be that from a quantum system I have a behavior, a Boltzmann-like behavior for the density, then mathematically I go that way by choosing appropriate set of observable, namely if a gas is sufficiently dilute, then I take the number in a small cell in a single particle phase space. So that's no objection whatsoever. It's a piece of mathematical physics, I mean that. But like was said before, this is not by itself a solution of any conceptual problem. That's why at the end you mentioned the the model, or somebody appealed to something else. I mean, this by itself does not solve the Schrödinger curve.
No. Not this
The approach
kind.
is nice. The approach is what we do with statistics.
The fact is that this is not to. This is not.
I don't understand limit. A limit, if you go really, it's really closed system, there is no limit. It will never come to equilibrium. So what do you mean by
In a
limit?
course graining, see. In a course graining, you have.
There is intermediate time scale when
Yes.
it looks like
Classical like.
I would not call it limit. Limits, it's time go to infinity and then it doesn't work.
No, it doesn't work. It works in that scale.
As mathematicians, we usually tend to make a limit to make precise what we just say. But I know that the universe is closed, so there is no conversion to equilibrium. There is in a certain time scale. That's all.
Yeah.
And then eventually the system continues to go back to.
But
then it doesn't sound like a limit. So it's like.
well, I never. It is interesting.
No, Boltzmann limit, because in classical mechanics, when you put in the irreversibility by hand, and it's there, then there is a limit.
You don't put it by hand. You just have an initial condition. Boltzmann show the overwhelming majority in a certain limit go be the solution of Newton equation get close to the solution of Boltzmann equation.
But this is Gibbs.
Case, you derive Boltzmann equation in a very similar way.
But this is Gibbs even. In Gibbs' approach is even clearer, because in Gibbs' approach you have all the scales of instability, and you can define the limits. They are coarse graining limits, of course. There is no magic. If a state evolves unitarily, has no limit, of course. But if you make a coarse graining on that system, on that state, you can obtain limits. I mean, this is well, you can. Yes, of course. This limit, practically, not mathematically, but practically, will be useful in a certain time scale, of course. But what I will, because we have to go to lunch, I would like to say one thing, that perhaps there is a kind of this difference in our viewpoint about what foundational problem means, especially in quantum mechanics. For us, I mean, we have people working in the limits between physics and philosophy, and sometimes those limits, for me, are not interesting. I mean, I'm not interested to know if what we do is physics or philosophy, but we always have a conceptual viewpoint. So if we are interested in decoherence, we are interested in decoherence from a conceptual viewpoint. I mean, there is something in physics, and we want to understand and to discuss the meaning, the conceptual meaning of this phenomenon. Perhaps it's not linked, just you were waiting with interpretation, but it's linked with a conceptual part of physics that sometimes is not discussed enough in physical communities, and sometimes they don't want to hear it. This is what I want to say. This is something, a kind of sociological problem, that when an idea is so established that they don't want to hear something different. But we can discuss with lunch. Thank you.